All right, so for a quiz, we have the equation or the function y equals x minus 4x plus 6 is x minus 8. Everybody sees that the zeros are x equals -6, put them in order, 4 and 8. Okay, which means you can start drawing the graph right away. Okay. Put x equals 8 here. You'll put x equals -8 here, although we won't need it. So then x equals -4 here. X equals 4 here. Gives us a pretty good idea where these things will be located. 0 at 4, a 0 at 8, and a 0 at -6. Agree with what you got? It's kind of what your graphs look like. You know, scales might be even worse than mine. Or they might be a lot better. But there they are. Okay. Now, if we're going to graph this thing, y-intercept occurs when x equals 0, right? So I don't know if you did that, but that's something you always do when you're graphing these, okay? Didn't ask you to do it. But if you're gonna do the graph, you would do it. So if you let x equal 0, you end up with -4 times 6 times -8, right? Well, 4 times 8 is 32. You got two minuses, it's gonna be positive. 32 times 6 is 192. So here you got y equals 192. And you got the y-intercept. Okay, now what's the whole graph look like? Well, you know, most people that drew the graph said, okay, well, it comes up from here and it has to somehow go through here. And maybe it kind of peaks there, probably not. There's a strong tendency to put the peak wherever there's an X, but it probably peaks a little bit to the left of that mark and probably a little higher. This is already coming down a little bit by the time it goes through here. But we don't worry too much about that. You learn when you take calculus quite a bit more about these graphs. Like you learn to know what, figure out what this point is, what the top high point is here. You get the slopes, and it's all pretty easy once you learn a little bit of calculus. Okay. But for right now, we just want to get this shape and be able to talk about these things. Now, why does it go down here and why does it go up there? I don't know that your text and your open math materials told you why. I think they just said use some big numbers. Okay. Something, am I right about that? To get the long run behavior, you just assume some big numbers. Unfortunately, I didn't have a chance to review exactly what open math said just because of my internet problems. Okay. That's one disadvantage of having your course on the cloud. We're fine till a hurricane. Okay. Which fortunately didn't kill anybody in this area, but Kuwait sure did wipe out some time. All right, so there we have it. Well, what I'm going to say is, if you expanded this, you can see that this would equal x cubed plus a lot of other stuff. We see that? Because you're going to have to multiply this x by this x, and that'll eventually be multiplied by this x, and that's the only way you're going to get 3 x's for an x cubed. So it's got to be an x cubed. Okay. Now, what does the graph of x cubed look like? From a distance, the graph looks like this. It pretty much just looks like y equals x cubed. And as I think I've said in here before, they just use the word wiggles. Here's some wiggles. You got the wiggle. Where are they here? Well, this is a big scale, okay? The interval from -8 to 8 might only be the width of a dot if you zoom back on this thing, okay? So you got some wiggles. You probably can't even see them. But you understand, if you're looking at this thing from great distance, the interval from -8 to 8 would almost disappear. Okay, go back far enough here, I wouldn't even be able to resolve it. Okay. But if you get to just the right distance, maybe that interval from -8 to 8 is about that big. Okay. But outside that interval, it acts like y equals x cubed. And what does y equals x cubed do? It comes up from here and it goes up here. So you just got to know what the shapes of your power functions are. Does that make sense? And you know x cubed, at least you did when you did section 1. We haven't talked about how to graph it. I am going to talk a little bit about that, time permitting. As a matter of fact, maybe I'll talk about it right now. Okay. To graph x cubed, you know that if you cube a positive number, you're going to get a positive. If you cube a negative number, you're going to get a negative, right? So this graph is going to be inside a rectangle like so. As usual, we'll go from x equals 2, -2 to x equals 2. Now, what are the y coordinates? Well, if x equals 2, x cubed is 8. So we got y equals 8. The y coordinate down here is y equals -8. Okay. If we subdivide this, we get y equals 4. Subdivide this, we get y equals 2. And y equals 1 is way down here. Now, why is y equals 1 important? Well, if we subdivide here, get our line x equals 1 and our line x equals -1, then the point for x equals 1 is going to be here. And the point for x equals 2 is going to be here. And of course, it's going to be 0 when x equals 0, which gives you a red dot in the middle of a big old rectangle. Okay, that makes sense? And then if you do the same thing on the negatives, I'm not even going to label them, but right here will be your line y equals -1. You're going to have a point through -1 and a point through y equals -8. When x is -1, y is going to be -1, and so forth. So your graph is going to look like this. I'll come up here, and we didn't even put in x equals 1/2, because to get x equals 1/2, you would have to do 3 more lines between y equals 1 and y equals 0. Every one twice as close to the x-axis as the previous, which means that that line is going to be microscopically separated from your x-axis. You can't even see it. Okay. Now, among other things, that means that the graph practically hits the x-axis by the time you get to x equals 1/2. So the graph is going to come up here. It's going to get very flat. And then it's going to go back up like this. Does that make sense? In terms of the way we've constructed graphs, that should be a compelling picture. So that when you draw this thing, you'll make it flat in the middle instead of drawing it like this, which is what I see a lot. If you draw it like this, you're missing the important thing that it flattens out in the middle. So it's this, not this. Hey, look what happens in here. Look what happens in here. All right. So that's your cubic function, right? And that's what governs the behavior of any polynomial of degree 3. It's going to be wiggle within a cubic function. And you're going to show the wiggles more than you show the rest of this graph, because that's where the interesting stuff really happens. Okay? So you kind of focus on the wiggles, but you know what it is outside the wiggles. So you know that it comes up from here and goes up to here. Now, if it's a negative x cubed, well, you'd have to reflect this thing and it'd come down like this and down like this, right? And it'd come down from here and then it'd go down over here. Well, just to make sure we understand, I'll show you what happens for y equals x to the fourth. Now, for y equals x to the fourth, if we think about it, we know that the numbers are always going to be positive. So we don't have to use any negative numbers. So here we can have y equals 0. And up here, well, this is going to be at x equals 2. This is going to be at x equals negative 2. We're going to have y equals 16 up here. Okay? And then, of course, we have our line x equals 0, which is just the y-axis. And x equals -1 and x equals 1. I'm not going to label them, you know what they are. Okay? And we could use -1/2 and 1/2. But that's not going to be practical. You're not going to be able to locate the point. Okay, well, anyhow, so we subdivide here and here and here, and we get y equals 4, and y equals 8, y equals 4, y equals 2. You get y equals 1, we've got to come way down here. And I'll label that one over here. And now we have our points. I have a point here because if you do the fourth power of -2, and we're doing y equals x to the fourth, do the fourth power of -2, you get 16. And if you do the fourth power of 2, you get 16. You have the symmetry about the x-axis. The graph comes all the way down to here and here and here. So, and it gets really flat between here and here. So it's, okay, if we start here, it's really flat, really flat for quite a ways. And then it turns kind of suddenly and goes up here and keeps getting steeper and steeper. Comes down like so. And turns pretty suddenly and flattens out. It looks a lot like a parabola, but it's flatter in the middle and steeper on the side. I don't know if you can read that, but it says like a parabola, but flatter in the middle, steeper on the sides. If you do the power functions, y equals, okay, x squared, x cubed, x to the fourth, the sequence looks like this. Okay, so here's your x squared. Here's your x cubed. Here's your x to the fourth. And what's x to the fifth going to look like? It'll look like this one, like this one, or like this one. Okay, call this 1, 2, 3. It's going to look like more like 1, more like 2, or more like 3. gonna look like 2. Why? Because you're taking a fifth power. If you take a fifth power of a negative number, you're going to get a negative. So it's going to have to be negative over here to the left and positive over here to the right. The difference in the shape is it's going to be flatter in the middle because it's going to get up there almost to 0 quicker than this does. Okay? I'm not going to detail that because we've got a lot of things to talk about today, but that's what happens. So it looks like this, but it gets even flatter. So maybe might exaggerate the flatness of it. It's going to turn very suddenly, stay very flat, and then turn very suddenly. It's going to be steeper on the sides and flatter in the middle than this one. Just like this one is steeper on the sides and flatter in the middle than those two. So that's what your power function looks like. And you can construct them. I just showed you how. That construction's easier than the constructions we've done because you use actually fewer lines. Well, actually, you'd have to subdivide another time to do x to the fifth, and you'd have to do that on both sides, right? So, you know, that would be tricky to draw because the y equals 1 line gets closer and closer and closer to the lower edge of your rectangle, okay? Now, I say that because every polynomial function is embedded in something with one of these shapes. Okay, you're usually not going to look at polynomials of degree 5 or bigger. But we'll go up to degree 5 here. And the only difference then is you keep alternating kind of a concave up shape with a concave down, then concave up, right? Getting flatter in the middle every time. Okay. But still maintaining a smooth curve as best you can. Eventually, it's almost like you draw a right angle. Okay. But you're unlikely to encounter polynomial functions of degree more than 5 unless somebody's trying to trick you or something. Okay, they occur, but there we have it. That makes sense. So just like we think of this as being embedded in this picture, you know, the overall picture with the wiggles in here, you know, all the stuff that we see here, any wiggles that occur are going to occur near the middle, and the wiggles are going to occur because of zeros. Now, what I said isn't quite right, but for right now, you can kind of take it that way. Okay, you can have wiggles that aren't zero. You could have a wiggle like up here and down here and up. If you just raise this thing up a couple hundred units, you don't have zeros here, right? You've still got wiggles. Okay. And we call these relative maxima, relative minimum. A relative maximum here, relative minimum here. Plural of maximum is maxima. Plural of minimum is minimum. All right. Actually, go for recording. Yeah, we are. Things. I got messed up. I think I messed it up. I don't think necessarily did it itself. Although I don't underestimate its ability to be tricky. Okay. Now, makes sense. You can kind of put things in context. The whole thing about long run behavior is just this behavior. You don't have to plug in big numbers that you're not going to understand anyway. I mean, you might understand that they're big and you might be able to connect that with the graph getting steep. You probably can. But with these constructions, it's much easier to see. Another thing is, if you go real close to this minimum here, in this case, it's just, for a little while, it's almost a perfect parabola. It gets lopsided because the zeros are spaced unevenly, right? And because you're coming up from here and all that stuff. So, you know, it's not a perfect parabola, but if you look at a little tiny slice of it and zoom in on it, it is very close to a perfect parabola. That's important to know. It helps you understand things that are just rules. If you understand the rules, you apply them, that's fine. But if you really understand it more deeply, that's even better. Now, I think I've shown you think I showed you last time, I know I did. This polynomial, right? Okay, just let's say a little more about it, but I'm not going to go into all the detail I did 2 or 3 times in the support course. Okay, just deals with it. They go around the circle, and if it goes around fast enough, the penny flies off. Somehow went into the cup, but it couldn't have happened. Great mystery as to how that happened, because it violates all the physics. Okay, and I'm sure of the physics. There's got to be something weird that happened, gremlins or whatever. Okay. So that's a polynomial. We want to find out when that polynomial is 0. Now, here's the polynomial written this way. And here it is written with the x instead of the psi. So that looks like something that you might see in an assignment. Okay. I'm not going to assign you that. Numbers are a little bit unwieldy, but it's just numbers. Okay. This is a polynomial of degree 4. What's its graph look like? Graph is going to look something like this. Maybe with some wiggles. I'm pretty sure, I'm very sure that there's going to be a wiggle somewhere, there's a 0 somewhere close to x equals 0.64. I could tell that just by looking at what angle this thing has to be for the thing to go to the cup. That's what that thing is, cup. Okay. Starting to lose words. So other ways I know this. I'll come back to this example. We're not going to do a lot of analysis with it. However, where we're going to go with this, with these polynomials, is this. And this is worth understanding. Okay. First of all, polynomial has a graph that looks like that. And when we graph it, we're going to concentrate on the wiggles. So it has a couple of wiggles, probably going to look something like this. Okay. Might not have that many wiggles, I don't know yet. I just haven't had time to mess with it that much. And everything I've done with it so far is all calculations, all been in my head. Okay. What I say here is, okay. Yeah, right. Here's the graph that I drew. Like a 4th power with wiggles, because it's a 4th power polynomial, degree 4. It has a 0 near 0.64. So if it has the graph that looks like this, then this might be your 0.64 right here. Okay. Now that's real small. You can see if you look at the video, but I say if this polynomial factors, then one of the factors should be close to x minus 0.64, because that's how you get zeros. Okay, in other words, if x minus 0.64 is a factor, then x equals 0.64 is going to be a 0. Just like in this polynomial, x equals 8 was a factor, right? Because x minus 8, well, x equals 8 is a 0 because that makes this factor 0. This factor is multiplied by everything else, and that makes everything 0. Okay. So I already know something about the graph of this. This means, well, over here. Here's a polynomial. X cubed plus 7x squared minus 5x minus 3. Okay? If you plug in x equals 1, what do you get? Well, x cubed would be 1, 7x squared would be 7, 5x would be -5, and -3 is still -3. 1 and 7 adds up to 8, -5, -3 adds up to -8. Okay? So there it adds up to 0. So P of 1 is 0, and we easily see that. I just made it up. I just figured out what these were and then subtracted it. Okay, could have done it for any number, but did it in my head, kept it as simple as I could so I didn't screw it up. All right, that means if you divide this by x minus 1, you're going to get a polynomial of degree 2. Why? Well, because x divides x cubed, giving you x squared, right? Well, I'm going to say a little more about that. Okay, to do the division, we do this. It's a long division. Okay, it's pretty simple. We start by dividing x into x cubed, and we get x squared. Now, x squared times x is x cubed, right? And x squared times -1 is minus x squared. So we put the x cubed under the x cubed here and the minus x squared under the x squared here. And we're going to subtract these. It's just like the long division algorithm you learned in 5th grade. You probably haven't used twice since then because you can use calculators. It's an important algorithm. But anyhow, you do that. So you put a little minus sign here because this is plus, but you're going to subtract it. Put a little plus sign here because this is minus, but you're going to add it. And you get 8x squared down here. And this gives you 0. And then x goes into 8x squared, 8x times. You multiply that by x minus 1, you get this, and you go on. I'm not going to go through the algorithm right now, but it's a pretty simple algorithm. All you got to do is practice it. Open Math will show you details. I'll go over more detail when we actually get to it. Okay? The point then is that now that we found that 1 is a 0, we can divide this. And now we know that the polynomial equals this times this, right? Because you multiply the divisor by the quotient, you get the dividend, the original expression, right? In other words, this divides this many times because this times this equals this. All right. We then conclude that x cubed plus 7x squared minus 5x minus 3 is x minus 1 times x squared plus 8x plus 3. At that point, we can set this, we can solve the equation, the polynomial is equal to 0. That's equivalent then to just setting this equal to 0. This is equal to 0. How do you find when this is equal to 0? Well, you set x minus 1 equal to 0. That'll give you the 0, right? Solve that, you get x equals 1. You set this equal to 0, and it gives you a couple more zeros by the quadratic formula. So now we know that this polynomial has zeros at 1, -0.4, -7.6. These are approximate because we're dealing with the square root of 13, which could go on infinitely. Yeah, that infinite number of decimal places with no real pattern. Okay? So you never get it exact no matter how many decimal places you use. I just use these to represent it. Well, you can graph that now. You know, you're going to have a 0 at 1, 0 at -0.4, 0 at -7.6. You also know that this polynomial then is approximately equal to x minus 1 times x plus 0.4 times x plus 0.6. Because -0.4, -0.6, and +1 are your zeros. So you can look at this and see, okay, the zeros are going to be at 1, -0.4, -7.6. These two being approximate. That little wave equal sign means it's approximate, okay? So we're back to where we started. Go back to what you did for the quiz and did correctly, at least up to the point of plotting the zeros, right? And the rest of it is pretty easy. So right there's our graph. We just embed it in one of these. So we know it comes up from here and goes through the first zero. It peaks and that goes through the next zero. And then it comes back and goes through this zero. Okay, or this intercept. We also know that if x equals 0, y equals -3 because 0 cubed is 0, 7 times 0 squared is 0, 5 times 0 is 0. So we get the y-intercept for free. If you have a polynomial written like this, right there's your y-intercept. That makes sense? Plug in 0 and that's all you're going to be left with. If it's in factored form, that's not bad. You can just multiply this by this by this. Okay. And let's say you're going to get -7.6 times 0.4, and that's 30.04. Okay. So these are pretty good approximations. That was just luck on my part. I knew it was close to 0.4 and 7.6, but I didn't know it was that close. Now that's the scheme. That's where we're going in the next few sections. Okay. So I want you to see that and understand that and understand why you're doing what you're doing. So that might be all I say about polynomials today, even though that's really what we're getting into, because I do want to make a couple of comments on the test and those new problems. And I just gave everybody a copy of several of those problems. There's some editing errors in that document that are kind of easy to fix. All right, so we're looking at a problem that comes up with the test. This would be the first version of number 114. That appears here. I also have put a solution to that one. I think it's actually maybe 117. I did a fairly detailed solution, or maybe it was 115. Okay, and it's posted if you need to look at it. But it's really pretty straightforward once you get over the idea, or once you get the idea that you can represent information like this as 2 points on a graph. I give you the profit at a given time, and I give you another profit at another time. And then I even prompt you, and I won't always prompt you, but on this test I certainly will, okay, to do this on a graph of profit versus time. Okay, well, this is a graph of profit versus time. If I say something versus something else, the first something goes in your vertical axis, the thing that versus goes on the horizontal axis, okay? So I'm going to even vertical axis is going to be this. Horizontal axis is going to be this. Otherwise, your fundamental triangle is not going to tell you what you, not necessarily going to tell you what you think it's going to tell you. You're going to get the run over the rise, instead of the rise over the run. Okay, so, okay. Now we have, here we have 100,000, we have 80,000. If you read ahead a little bit, the problem asks you to estimate when the profit would be 120,000, okay? Now that's kind of convenient because if it's a linear graph, a straight line graph, it's going to take, it takes you 3 months to go from 80 to 100, right? Then to go from 100 to 120, it's going to take you 3 more months if it's linear, if the rate stays the same, right? Well, you can figure it out that way, but you're not getting credit for it unless you use the equation. Okay, I want to see the equation because sometimes the numbers come out so any fool can see it without knowing anything about the equation of a straight line. Okay, so you got to get the equation of the straight line. What I'm really testing is several things. can you get the equation of a straight line given 2 points? Well, first, can you get 2 points from some situation information, right? Okay, then can you find the slope? Can you find the rate of change? That's 7 points out of 10 right there. Okay. So let's do it. Okay. Now you go up to the 9th month, but you know you're going to go a little bit beyond that if you're going to find out the profit at 120. You don't necessarily need to do that using the graph, but it helps if you can see the graph. So I'm going to put t equals 9 here. And I'll put t equals, I can divide this into thirds. Here's where t equals 6. Here's where t equals 3. Just approximately. Okay. Other thing is, if you completely label the graph, I might be forgiving of some other minor details you miss. So I want to say t is time in months. And p is profit in dollars. I wrote that kind of point. I have to be able to read it. But that really specifies for anybody that looks at this graph what everything means. Okay. Okay, then we got to put our profits on there. Well, profits are on the vertical axis. They're going to correspond to horizontal lines. So profit of 100,000, I'll put right. Instead of writing all the zeros, I'll write 100K, making 100,000. Everybody okay with that? Okay. And then again, I expect reasonable locations of these points. Okay. If you put it a little higher, a little lower, okay. But if you think 100K is here and 80,000 is down here, you got, if everything else is right, I'll probably only knock a point off, go to 10.12. Okay. Okay, so there it is. Well, that gives us 2 points. Okay, so that this point is $680,000. This point is 900,000. Now you got a straight line. Now that straight line probably doesn't go on that way forever. If it did, you'd be up to profit $1 million in a few years, right? And hopefully, yeah, it's your business. That's great. Okay. But profits are going to continue to rise forever in a linear rate. And it's probably seasonal. This is like between June and September. Okay. So maybe that's your busy season. Maybe your business caters to summer stuff. Okay. So your profit's going up as the summer goes on, but then the weather's going to turn. So pretty soon it's going to start falling. It's probably not really linear. We're talking about an average rate of change, right? So you don't take this straight line too seriously. But between here and here, it's going to probably be close to whatever's happening. If things curved a little bit, the straight line's still going to stay close. Okay, what's good to know that? Okay, so what next do I ask? Well, let me do questions in order. I think the next thing I ask is you do fundamental triangle. Yep, use a fundamental triangle, get the rate of change. Now, what we do? Use a fundamental triangle, get a rate of change. We first sketch the triangle with the arrows, what we've done. Okay, and then we label things. Now, if your graph is as small as mine, it might well be. We bring picture down here, make it bigger. Now it's inside the circle. Next, this point, And this is I think it's really helpful if you draw these lines and label them, because then you can clearly see what's happening. Takes a little extra time, but it doesn't take long. Get in the habit of doing it, you're gonna get things done quicker because everything's gonna be clearer. It's worth taking us a little bit of time to label these things, so now we can see. It's still pretty small. I wrote that pretty small. I just say run equals 3 months. You really want to kind of label it even a little better. Yeah, make it a little bigger. You can say like that, right? Run is 9 minus 3 is 3. Time is in months. And this is your delta t, right? You're not going to find the slope. We're going to find the rate of change. Of course, it's the same thing. Hundred K minus 100 minus 80K equals 20K. Meaning $20K, $1,000, right? Now, when we start doing calculations, we'll write all the zeros in the center, okay? So that the rate of change is delta y. The average rate of change of profit with respect to time. Average rate is delta P over delta T. $40,000 over 3 months, right? And I put the dollars and months there so I know what it means. So I can say then the average rate okay. Hey, don't put a dollar sign in front of this because you spelled out dollar too, right? Everyone do dollar sign over month. No, people would know what that means. And you read that as dollars per month. Okay, now you want to find the equation of the line. Well, first, I said use a formula to find the slope. Okay? I usually won't ask you to use a formula to find something unless there's something that actually gives it the meaning. So the formula, like y2 minus y1 over x2 minus x1. But in this case, it's not y, it's p. It's not x, it's t, right? Okay. That's 100K minus 80K over 9 minus 6. That's what the formula says. Coincidentally, That's the same thing we did to get the rise and the run, right? Now, at this stage, I probably want to put the units, dollars, months, and the average rate and the slope are the same thing. Okay, give you the same thing. The formula gives you the same thing as the fundamental triangle. I don't want to see the triangle. I don't want to see the formula when you're doing the triangle. I don't want to see the triangle when you're doing the formula. Okay, two different ways to see how these two things are the same. And this is a separate concept of calculus. We're right on top of it. Okay, I have to do it for instantaneous changes and stuff like that. And you can worry about that when you get to calculus. This is pre-calculus. But you should be very well prepared to understand what a derivative is telling you if you understand this. Okay? And you should also be well prepared to put a real world problem onto the graph. Okay? Those are two really important skills, and they're not that difficult. Matter of fact, everybody did it just now. Okay? I do ask you to explain why the slope and the average rate of change are the same, and I'm going to tell you how to explain that. I want to see your own words. I'll grade it fairly leniently. You make a good attempt to tell me, I won't ding you. Okay. Give me a really good explanation. I might let it cover another sentence. Okay. Okay. Now find the equation. Well, slope is 6,667. Okay. Meaning $6,667 per month. If y equals mx plus b, that's your standard form. Okay. But instead of y, we're using p. Instead of x, we're using t. So mt plus b is a pretty common form because a lot of things are changing in time, and a lot of graphs have time as the independent variable. Okay, so t equals mt plus b. So we have this. T equals 80,000, t equals 6. So there we have that. We solve for p and we get b equals, no, I think it'll be 50,000. Wait a minute, yeah, that's 30. No, that's 45. Okay. Multiply this by this, you get about 40,000. And then subtract that from 80,000, you get this, and that's very straightforward. Everybody would do that if you understand this scheme. And at least a couple of days ago, or a couple of classes ago, everybody understood this scheme for finding the equation of a straight line and used it in reference to the formula. Now, there's also a formula for finding the equation of a straight line. Y minus y1 equals m times x minus x1. Okay? Use that if you wish. Somebody say something. Everybody hear something being said? So I'm not hearing things, right? I forgot to take my medicine this morning, you know. Okay, somebody on the hall. I couldn't tell where it came from just because of the way my head was turned. It was either directly in front of me or directly behind me, but I couldn't tell which. Okay, just kind of, okay, anyhow, we understand. All right, this is a function, P of T equals. Don't have to write P of T, but it's useful to understand that this is function notation. And that's a useful way to express it, okay? Okay, so now, when does profit exceed $120,000 per month? You know, if I was doing this and I had the graph sitting there, I'd say, okay, well, let's see, let's just. My blue chalk. There. Okay. So. That's the line for people's P equals 120,000. So let's say we made the estimate of T equals 11. If you have an accurate graph, you see that this interval is the same as this interval. If it's a straight line, then this distance would be the same as this distance. Would really be T equals 12. But let's just say it didn't estimate, got T equals 11. Just to illustrate what often happens. If the numbers are trickier than these, yeah, your graph is just going to give you a ballpark, and then you can compare that what you get when you solve the equation, right? Well, this is a solution. Of P equals 120K, right? We know that if we get 30K out of our solution, we did it wrong. Okay? That means either we have the wrong equation or we did some bad algebra. Now, I don't think you're likely to do bad algebra for this because it's really simple. But first, you got to write the equation. So maybe you write the wrong equation. Why does it profit 120K? And actually, I didn't say P of T. Let's make sure we can do this interpretation. What is a profit? 120K. Well, right there, profit is your P of T in terms of T. So P of T is going to be 120K, T is going to be flat. Okay. So you do that, you're going to get 12. Now you round it off. The 6667 is actually 666 0.6666, and yeah, just repeated sixes. So from the round up, you're not going to get exactly 12. That's okay. But you're going to probably then see from the graph, well, it's got to be 12. Okay. We'll find touch to put on that. This assumes the trend remains linear. This trend starts to, curve down because it's fall. Okay. Then this is going to hold up. It's an extrapolation. We're extrapolating that it would be 120K, but that might not be the case. And then what would be the expected profit in month 12? Now, this randomization of these problems, it just so happens in this case, this is just redundant with what you got here, right? As you said, the profit will be $120,000 in month 12. Then it asks, what will the profit be in month 12? It won't always work out that nicely. It could have said when's the profit in month 11 or something like that. Okay. And then is it reasonable to expect this model to apply for a period of several years? Explain your reasoning and so forth. So I want you to think about that. Okay. Now there are 3 other versions of the problem. You can read them here. Couple of errors, at least one that I can spot pretty quickly. On 117, you're talking about a car coasting up an incline. And 7 seconds after your clock starts, it's gone this fast. And, 12 seconds after it's this fast. And you're going to put that information on a graph. But then lower, it asks you to use the equation to find the month at which the speed would first fall below 15 miles an hour. Okay. That's an editing mistake because I used the solution, I used the first problem as a template for all the others. And I just didn't, I edited, instead of profit, I gave you speed, I used different numbers and time in seconds and stuff like that. And I missed the month. Okay, that should have been time in seconds, right? Now I'm going to go in and look at the tests and, just kind of pen in the correction on that, on the test where that occurs. And then I think that I used month again on number 18 when it should have been year. So there are 2 places, 117 and 118, that I used month instead of year. And there might be other things. The version I posted online with a lot of information, you should read that. And I've made all the corrections that I could spot, which are just that one. There's another one, I forget what it is. But you can use that. It also tells you that first problem, 40 points. And then there's 6 more problems, including a problem in this set. The numbers will very likely be different than the ones you see on the samples. Okay, although by coincidence, it could be that you get the same numbers, but don't go in expecting it. All right. And then the last problem, okay. So there's a 40-point problem, then you got 6 10-point problems. 40-point problems, one you know, okay, about the graphs, all that stuff. What we've been talking about all semester. Randomly, it's going to be quadratic, exponential, or reciprocal function. People did notice that they had more problems with reciprocal function than the other two. That one kind of tends to throw them. Well, yeah, we did that in detail in class. Just had a little extra time preparing that. It's really no different. You just have to know how to draw the graphs, which you did. Okay, and make sure when you go in, you know what the rules are, how to draw those graphs. I guess that's. Okay, the last problem is a 10-point problem. So this is only a 10-point problem, but it should be an easy one. Because, you know, y'all were right on track with it when I had to take up the quizzes. If you do well in this problem, because I think it's a real important problem, I'll make it a 25-point problem if it helps your grade. Okay. So there'll either be 100 possible points or 115 possible points. Well, your grade is what you score divided by how many points there are as a percent. And it tells you that. So read that document. It's already linked to your page. I put it up there yesterday. Fair enough? I expect y'all are going to do pretty well. If you take the time, you do all the preparation. You certainly have the aptitude to do it. Okay?